Now there's this session 2 on data distribution. We have our speakers, Shaistha, Fathima, and Sneha, Saxena. Shaistha is an engineering student and Sneha is a data scientist at Grubhub. So the next session is on the session 3 is on May 14, Saturday, same time, 11 a.m. EDT and 8:30 p.m. IST on regressions and prediction. So we hope to see you there. And Sneha, over to you. Thank you.
Thanks, Anjali. I'm just going to take 1 second so I can start sharing my screen, and then we'll get right into it. Okay. I just wanted to call out that I am unfortunately a little bit under the weather. So if you hear me coughing or pausing randomly, please bear with me. Okay, without further ado, I'm gonna get into what we are going to cover in this session. Here's a high-level agenda. This session is all about the data distributions, which is like one of the foundational elements of statistics related to machine learning. So we're going to touch upon what is data distribution, what are some applications. We will talk a little bit about the normal distribution and central limit theorem, which some of you already must be familiar with because it pops up in a lot of literature, articles, videos. It's kind of one of the most popular distributions. Then we will go into a deep dive around some of the most useful discrete data distributions and continuous data distributions. All right, so what is a data distribution? It is just essentially a function that will give you all possible values for a variable and their frequency. So there seems to be like a lot of terminology packed into this one sentence definition. Let me break it down a little bit to you guys. Basically, when you think about data with respect to modeling, or you're just exploring some data, right? You want to understand how many points in your data set have certain values. And you want to kind of visualize that and plot it over an X and Y axis. And then you see some sort of a curve or some sort of a distribution. Essentially, that is what we are talking about here. And there are certain standard distributions and certain predefined formulae that tie into these that are very, very applicable in different scenarios of machine learning. The graph that we see here kind of highlights some of the more popular ones. One thing I want to quickly point out, if you look at this graphic here, you see like a bunch of graphs or distributions with names on them, right? Some of these you see will have bars in the graph that are a little far apart from each other. So those are the ones that are your discrete data distributions, for example, binomial, Poisson, geometric, uniform. And when you look at the ones kind of at the bottom, you see that the bars in the graph are more closely packed, which are your continuous data distributions. So the normal distribution, which is also called the Gaussian, students t, chi-squared, or these are the ones that we will be talking a little more in depth about today. But outside of that, you have the exponential and gamma distributions. All these are the ones that are more commonly used, but these are not the only data distributions that you can find for your different use cases. There are many, many more, but these are the ones that are most common. So before we get into kind of the weeds of it and talk in detail about specific data distributions, I quickly wanted to take a step back and understand what it really means from a kind of foundational or a conceptual perspective, right? So, and I hope this image with all the math and everything is not scary, because it really is not, and we'll walk through this example. Essentially, there are two key elements when you think about data distributions. One is the variable itself, which we call a random variable. The other is the distribution itself, which essentially is giving you the frequency for the different values that the variable can take, right? And when we say frequency, we are in some sense trying to get to a probability distribution. What is the likelihood of the variable taking value 1 or 2 or 3 or whatever that might be? So it's just about that. Now, if you think about the random variable, it is nothing but the different values that can occur in your specific event or your test or trial or experiment. Now, when we say experiment, it doesn't have to be like an actual statistical experiment, but in statistics, we just give it the name of experiment or trial most commonly. And it can be something as simple of just flipping a coin and getting a head or a tail. That itself is a trial or an experiment. It can be something simple as from a deck of cards, picking the queen of heart or something like that. And I'm talking about these examples because these are like typically used in probability and statistical literature. So it might be a little more familiar. Now, thinking about, I mentioned data distribution can be discrete and continuous. And where that really stems from is this random variable itself. So the random variable can be discrete and continuous. And we will see how that flows into the discrete and continuous data distributions. Now, what do we mean when we say discrete variable and continuous variable? When you think about the values that your variable can take, if you can count or there are like a finite number of values that your variable can take, then you say it is discrete. For example, in here what we see is we are flipping a fair coin. By fair coin, you mean there is equal likelihood of getting a head or a tail. And you flip it 3 times. That's our kind of experiment. And we talk through what are the different outcomes here. You can get all 3 heads, you can get 2 heads and a tail, head, tail, head, so on and so forth, all the way till you can get all 3 tails. So those are all the possible outcomes. So if we think about defining our random variable, in this case, we denote it as X, we say the definition of this random variable is the number of heads that you get after flipping a coin 3 times. You can define it any way as you like. It depends on your specific use case. So for the definition that we have, there can be these possible occurrences, right? You can either have 0 heads, which is in this situation where you get a tail, tail, and tail. Or you can have 1 head, or you can get 2 heads, or all 3 flips can result in a head. So there are 4 possible values that your X can take in this example. So that makes it a discrete variable. Now, when you talk about some other applications, for example, you're working for a company and your data has something like, let's say, revenues or profit. And your random variable models that particular aspect of the business, for example, revenue or profit, right? Now, your random variable in that case can take any number on the real number on the real number line, right? It can be 20.1234567, whatever that might be. So in that case, you cannot count or there is not a finite number of values that your random variable can take, which makes it a continuous random variable. And this is how the variable then goes on to construct a distribution. When you plot all the points and join them together and you see a distribution, it ends up being a discrete or a continuous data distribution. So I've already kind of touched upon what a probability distribution is through this example, right? Let me quickly kind of finish talking about this example and then we can move on. So here are all the possible outcomes that you can get when you flip a coin 3 times. And we spoke about the definition of the variable, which is getting ahead when you flip, after you flip the coin 3 times. And these are the possible 4 values that X can take. It can have 0 heads or 1 or 2 or all 3 heads. Now, without getting into too much details about probability, just how you would measure this probability of X being 0 or 1 or 2 or 3 is in the numerator, you will just look at the number of cases here that we listed where X is 0. And denominator, if you notice, is going to be same all across, which is just the entire universe of your sample, right? So here you have 8 total possible outcomes. So your denominator becomes 8, which is the entire sample size. And in the case of X is equal to 0, where we have no heads, there is only one possibility, which is all 3 being tails. So the numerator becomes 1. And the probability of X being 0 is 1 by 8. Similarly, if you look at X equal to 1, which means we have 1 head, now that we have here, which is head, tail, tail, and then here, tail, head, tail, and then tail, tail, head. So we have 3 possibilities where that can happen. So then you get 3 in the numerator and 8 in the denominator. So when you do this kind of an exercise for all possible values that your X can take, you get all these different probabilities. And then when you start putting them into a visual representation, on the X-axis, you put all the different values that your X can take, and you put the probabilities on the Y-axis. And then when you draw this out, you get what is your probability distribution. And in this case, it is discrete. I'll pause there to just check if there are any questions. Okay, awesome. So moving on, let's talk really quickly about the normal distribution, which is very popular as the bell curve, simply because it looks like a bell. We'll talk about what this distribution is, what are some interesting characteristics, and what are the applications of the bell curve. So this is also known as your normal distribution or your Gaussian distribution. What this is really is a curve or a graph that is symmetric about the mean. So this peak that you see here is the mean of that distribution. And as you can tell, the width or the height can vary. And that essentially depends on your standard deviation. So standard deviation, like we also mentioned in the previous session, is something that is related to the variance in your data, which indicates the spread of the data. The more the variance and the standard deviation, the wider your curve will be, which means the data is more far apart from the mean. And that kind of impacts your height a little bit too. But essentially, the mean and the median and the mode will all be in the same place where this peak is. The other aspect of the normal distribution is that it is a continuous data distribution. And like I just mentioned, it is essentially has 2 key parameters, which are the mean and the standard deviation, which help us in like defining this distribution. Talking about some of the interesting characteristics, it is centered about the mean. All 3 summary statistics, the mean, the median, and mode are equal in this case. It is a symmetric distribution. And like I mentioned, if you see in this graph, the mu is nothing but your mean. So in the top 3, the blue, green, and red, you see mu is 0, which makes all the 3 graphs here start at the same point or have the same center rather. The 0 here at the bottom, if you can see it, it's a little small. And the last one, the orange graph, is mu equal to 2, which means the mean is at the number 2. So the peak is right here, which is why you see this graph being shifted to the right. But the sigma here that you see is essentially the standard deviation. And the higher it is, for example, in this red colored graph, you see this is almost looks like a flat line. It's basically a normal distribution, but with a very high standard deviation. So it's like really wide. And this one has sigma is 0.4, so it is much more narrow, but has all the other essential characteristics being the same across the board. The last interesting characteristic I wanted to point out here is it helps us have something called this the empirical rule. And this is one of the things that makes the normal distribution really, really useful. What this means, or what this rule is, that when you have a normally distributed data, you can tell that almost 68% of the values are within one standard deviation from the mean. And then 95% values are within 2 standard deviations, and almost 98% of the values are within 3 standard deviations. So how does this help us is, when you know the mean and the standard deviation of your normally distributed data, and you don't know the rest of the data points, but you can kind of infer or predict where your specific point is going to fall with it. Is it going to be within the 68%? Is it going to be within 98%? Or is it going to be within the 95%? So that kind of gives us one of the most useful applications of this distribution, which leads me to my last topic, and then I will hand it over to Shaistha to talk about other discrete and continuous distributions. Normal distribution gives us a good foundation for the central limit theorem. If you go into any literature, you think about different examples, you will see that a lot of natural phenomenon have like a normally distributed, have a normal distribution, right? And central limit theorem kind of is useful because it helps us model that within our own data and use cases. So essentially what this states is, when you have n number of samples of data and you calculate the mean or the average for each of those samples, and you plot those different means or averages, the distribution of the means of samples is going to have a normal distribution. So why is this so interesting? Because even if the distribution of your population is not normal, it can be binomial, it can be uniform, it can be anything else. But when you take many samples of that data set and you get their averages and you plot those averages, you will see that the distribution of sample means will always end up being a normal distribution. And that kind of helps you with some of the assumptions that are there in either linear regression. It helps with hypothesis testing, because all these different methodologies and algorithms have underlying assumptions of data being normally distributed, or your standard errors being normally distributed, whatever that might be. Now, there are some assumptions to the central limit theorem. First thing is that the samples we spoke about should be randomly selected. There should not be a bias. Each sample has to be independent of each other. What that means is one sample cannot influence the other. And every time you pick a sample from, let's say you have 100 data points and your sample size is going to be 20. Every time you're going to randomly pick 20 numbers from 0 to 99. And then you put those numbers back, and then again, you pick another 20 at random. So that is called randomly selecting them with replacement. And that is what we need in this case. And samples have to be independent. The other main point about central limit theorem is that the samples, when they are large enough, the larger your sample size, the closer your distribution of sample means is going to be to the normal. So what does this large enough mean, right? Usually a sample size of 30 is considered good, but if not that, you can use like 10% of your population size, if you know that, as the sample size to achieve or to work towards your central limit theorem. Now, what is the application? Why is this so popular, right? In many cases, what happens is you don't know your entire population. You only might have like a sample of data. So you don't know what the population mean is, you don't know what the standard deviation is. What this helps you is in kind of estimating or predicting the characteristics of your population, which is the whole kind of goal of statistics, right? So for the central limit theorem, the average of all sample means gives you the population mean. The average of all sample standard deviations gives you the standard deviation of the population. And like we mentioned earlier, when we have the mean and the standard deviation, you're able to kind of reconstruct or at least estimate or predict the characteristics of the overall distribution. So that is where this is really, really helpful. And with that, I will pause for questions if there are any, and then hand it over to Shaistha to talk to the rest of the session.
I don't think we have questions
Awesome.
in the Q&A, so we can go
Okay.
to Shaistha now.
All right.
Yeah. Hey everyone, just a second. Let me know if you can see my screen. Yes, you can.
Your screen is visible, Shaistha.
Yeah, thank you. So, so far you have learned about random variables and all. Now it's a time you go deeper into like this types of data distributions, and they are usually of two types, which is like usually categorized into two types, that is discrete data distribution and continuous data distribution. And before you go deeper into what a data distribution is, it's important to understand what a discrete data is. A discrete data is usually a numerical type. That means it will be number, and it has to be whole and concrete number. For example, 1, 2, 3, 4, 5, like that. It cannot be decimal numbers such as 1.2, 1.5. It can't be like that. So an example of discrete data would be number of customers who bought different items from your store, or maybe the number of push-ups you can do each day, or maybe the number of items you buy at a grocery store. All of these are a whole concrete numbers, right? It can be 5, then 15, but it can't be 1.5, 1.25, something like that. So that's what a discrete data is. And yeah, discrete data has some another quality called qualitative quality. It's not only quantitative, that is, it has a quantity number, it can be specified with a number, but it is also qualitative, meaning it can have its own like futuristic kind of things as well. For example, when you fill a form and it asks you about your nationality, that's like the qualitative example of it. Maybe your favorite color, your mother tongue, your religion, anything which specifies something about you can be a qualitative description data. So how do you know if a data is discrete or not? Just as I said, it has to be finite numeric countable number, that is 5, 10, 15. It cannot be 5.5, 5.25, something like that. It has to be easy to visualize and demonstrate. So it should be easily be demonstrated using a bar chart, line chart, or a pie chart. It is categorical, meaning it can be something like gender of a person, nationality, favorite color, things like that. But the thing is, how does nationality helps? I mean, how would it be any use to know if what my nationality is? So it could be used for verification. Yeah, people use like, okay, you should be an American to be part of this certain program, but other than that, what other purpose could it have? Now, for example, if you were to if this was the same case when you were applying for a job, this could just looking through the workspace and going through the hiring process practices, we can know what kind of what kind of hiring practices are being managed, what nationality is being preferred, which is not, what's the density, and how is it, what's the proportion of people of different nationality within the workspace. Those kind of information can be achieved from that. So in a way, you can say that discrete data is distributed discretely in terms of time and space and can be used for more practical uses. Final thoughts? Just like finally, you can just think of it as it involves counting rather than measuring. It has to be numerically counting. And then one of the best use case based example for this would be national census, which consists of both qualitative and quantitative data. That means it does have qualitative features like nationality and all, and quantity like maybe how many family members do you have, things as such. And counting and collecting these identifying information can help us understand the population better and make better predictions for the future. So this is one of the use case of discrete data and how powerful it can be. In this, for this session, we are gonna look into 3 types of discrete data distributions, that is binomial, Bernoulli, and Poisson. Starting with Bernoulli distribution, which is one of the easiest distributions out there, and it's also like the founding distribution type of it kind of builds a foundation for other distributions such as binomial distribution, geometric distribution, or negative binomial distributions, which play kind of crucial role in deep learning. So the starting point to derive more complex distribution. It can be a starting point to derive a more complex distribution. And why would we think that? Bernoulli distribution is as simple as when you conduct an experiment, the answer should be something, should have only 2 possibilities. That is, it can either be yes or no, it can either be true or false, or something like this. There's only 2 answers to it, predefined answer, and only one of it could be the answer from that for it. So in other words, we can say that a Bernoulli trial is when a random variable can be 1 with the probability p, that is for success, and or it can be 0 with the probability 1 minus p, that defines failure. And a pass or a failure of exam can be modeled by Bernoulli distribution. So just to sum it up, a Bernoulli distribution deals with data which has only 1 trial and 2 possible outcomes. Anything other than that is not Bernoulli distribution. So the formula looks something like this, where n is equals to 0 indicates failure, and n is equals to 1 indicates success. What are the examples? Like real use case based example for Bernoulli distribution could include like success of medical treatment. How successful is it? Is the COVID vaccine, for example? Then the result, student results. Did they pass or fail the exam? Was the disease transmitted or not? The most famous one, coin flip, number of heads. Then your favorite sports team win or not, and so on and so forth. There can be a lot. Now looking at the, for example, let's take an example where we say that the, for example, we take an example of a football, where we said that if a player has a 75% success rate for kicking an extra point, which is denoted by 1 in the graph, and there is this probability of 25% denoted by 0, which is like it's going to be a failure. So the graph kind of looks like this, and this is assumed keeping
Hi,
in mind
Shaistha.
that external factors.
I'm sorry to interrupt you, but your voice is lagging a bit. So could you check if your mic is rubbing onto something?
Okay. Now can you hear me? Or
Yeah, it's clear. Thank you. Thank you so much.
Yeah, thank you. So so Bernoulli distribution in this example, like 0 indicates the failure rates of the kick, that the player was not able to kick an extra point, and 1 includes indicates the player was able to shoot a kick, which was a success. So now, in case of Bernoulli distribution, we usually keep in mind for only 1 trial, that is only for 1 coin flip, head or tail, only for one particular kick, what was the result, something like that. But if you want to summarize and pull it up for number of events, more like if I were to throw 100 coins, what would be the result, and you want to look deeper and dig deeper into that. That's when a binomial distribution comes in. So it's the number of success in specific number of tries, and those tries has to have a fixed number. So it can be a finite number of tries within a finite number of tries, and similar to Bernoulli, it has the same principle that the outcome can only have two possibilities. That is, it can be a success or a failure, yes or no, true, false, anything as such. Now, the below is a graph showing a Bernoulli binomial distribution for a number of point clips. Binomial distribution, like I said, can be defined as a probability distribution related to binomial experiment, where the binomial random variable specifies how many success and failure occurs within that sample space. So the time and the number of flips are predefined. And the formula looks something like this. And remember, in binomial distribution, the mean is usually greater than the variance. Binomial distribution. There are some requirements that have to be met by the random experiment to be called a binomial experiment. And these are the fixed number of trials, that's must. Each trial must be independent of the other. For example, the before trial was like if the kick was success in the previous trial and it's a failure in the next one, it's not really affected by the success of the previous trial or the failure of in the previous trial. So it has to be independent. Each trial must result in one of the two possible outcomes, that is success or failure, and it should have like constant probability of success for each trials. So the probability is usually constant, and it does not vary, like move too far away from the approximate like estimated percentage.
Shaistha, sorry to interrupt a little bit. Do you think your headphone is rubbing with something? So we are hearing like a windy noise.
Yeah, it was a fan. I just turned it off.
Okay, sorry about that. Thanks so much.
I'm really sorry. Now, no can problem. You hear? Is it clear now?
Yeah, it's absolutely clear. Thanks so much. Please continue.
Thank you. Thank you for letting me know. Okay, so one of the examples, like I said, the most famous examples is like tossing a coin. And if you do that for 50 times and you want to build a binomial distribution, for that, this graph looks something like this for it. What we are actually doing is flipping a coin and trying to find, okay, it was a success, failure, and plotting a graph for that and seeing the distribution. Okay, how did it go? How many success and all percentage for that? And this is for 100 coin flips. Other most popular examples would be like finding the number of defective items among the item you bought or among the item you have. It could be anything in the store, maybe looking for, you have mobile phones and you're looking for the defective ones. And that could be one example. The person infected with, is a person infected with COVID-19 or not? If a person suffering from disease or not? Number of voters voting for XYZ candidate, and so on and so forth. Poisson distribution. Now, Poisson distribution is more of similar to binomial, but it goes with something called in binomial, we were looking into the fixed set of trials, right? In Poisson distribution, it doesn't really depend on that. The success rate can be very low, but it can be among the infinite number of trials. It goes longer. So Poisson process, it uses a process called Poisson process. It's a model for a series of discrete events where the average time between the event is known, but the exact timing of the event is random. That means we know that something, the success might happen during this time, but we don't know when exactly it's going to happen and when the occurrence is going to be. So one of the examples would be like internet failures. When you don't know an internet failure might happen, but it can happen like within a year or a month or something like that, in an infinite number of time, but it does happen somewhere. Customer calling a help center, visiting visitors landing on the website. These do happen, but it's hard to determine when it is going to happen. And it cannot be put into a fixed frame where you can calculate it. So, the important things to remember here are, there are three categories that every example should fit in to be called like to be known to be fit for the Poisson process or distribution. That is, the events of each process are independent of each other. Every event should be independent from each other. The average rate of event occurrences per unit of time, say per month, is constant, and two events such as internet failure or non-internet failure cannot occur simultaneously. So only one thing can occur at a time. So Poisson distribution indicates how many times an event is likely to occur within a specified time period. So it can be, it's commonly used by, say, to find the probability that an event might happen on not knowing how often it usually occurs. For example, the insurance companies use it to conduct risk analysis and predict the number of car crash accidents within a predefined time span to decide on the car insurance pricing. Now, I've been saying that this could be within infinite number of trials, right? The trials are infinite number, but the time span, you can set it like within a year. I want to check, and I can do infinite number of trials. I can go and crash cars like just for testing if I want. I can flip like 1,000 coins, 10,000 coins, how many numbers I want to, but we can just put it in a time span of, say, 1 month, 1 day, 100 days, like that, to find an accurate, to be able to make some sense of the data. Poisson distribution formula looks something like this, which includes random variable from random variables, number of occurrences, Euler's constant, and expected value. Random variable. To make it easier, it looks something like this. So it's the event, it's the k events in the time period is equals to the event rate into the event rate per the event probability of k number of events. So what they're doing is just removing the event rate from that and this with the lambda, and you get this easier formula to remember. And if you look into, this is one of the sample of the Poisson distribution graphs, and say when the lambda is 1, the graph goes something like this in the yellow pellets. The lambda is 4 and lambda is 10, it varies. So when k is the number of occurrences, where p, this indicates the probability of k occurrences, and when the value is like 1, 4, 5, what's the probability of that? So how could this be used? An example where this could be used is number of earthquakes happening in a year in a certain area, the number of calls coming into a call center in certain interval of time, the number of buses coming into the station in a certain interval time. So notice that these things do happen, but we don't exactly know when it will happen, and we are putting into in a time span that just to get the make a better meaning of the data. Other use cases of the Poisson distribution includes it has a use case in a negative binomial regression, as it can be used because of the subintervals of the occurrences of the event in Poisson is compared similar to the trials of the Bernoulli, and it is used for the probabilistic models examples. It can be used to solve machine learning problems, which usually depends on counting variables and can be modeled using Poisson process. It can be used for time series modeling or for financial count data that, for example, to find in finance, to find a model with the number of trades that a typical investor will make in a given day, or to find out the shock to the markets. So just summing it up, Bernoulli distribution is simple. It is only for one trial with two possible outcomes. For example, will you pass or fail an exam? Only one trial. And binomial distribution is an extension of Bernoulli with two possible outcomes, but this time we have fixed number of trials. That means you can only we are choosing to find see the result for 50 flips of coin, and say for number of 50 students passing the exam or not. But when it comes to Poisson distribution, we go a little in a situation where we know success or something will happen, but we don't really know when it's going to happen. And we want, when I say when it's going to happen, it's after how many number of trials will it happen. So usually it's extremely small number of success chances. For example, printing mistakes on the pages of the large book. So it's very rare to happen. It could be like 1 in 1,000 papers. Earthquake in a city, it's also really rare, especially in a city which is not prone to earthquakes, something like that. That was all about discrete data distribution. Now moving on to continuous data distribution. This is completely opposite to discrete. This includes numerical data and can have unspecified numbers of possible measurements between two realistic numbers. What does that mean? So it can have it's more about accuracy. That means it will have decimal points. It goes it goes something like 1.2567, 1.7.7567, like that. It goes in the decimals as well. An example would be the weight of a newborn baby, daily wind speed, temperature of a freezer, and time taken for you to run 100 meters, and so on. So on. Continuous data can either be numeric or distributed over date and time. So it's easier to think that continuous data typically involves fluctuating numbers between two presumed points. So say start point and end point. What's, for example, if you're running 100 meters every day and you want to check into what's the time lapse every time, how much have you improved, things as such. Continuous data changes over time, just as I said, it changes over time. And for example, when you're running into running for 100 meters, and it just the changes might be very small, say 5.78, then it improved to 5.678, and now it's 5.654. As you can see, the changes are very small and the improvements are very small. But over a time, this change will become more apparent and can be bet into a new data point striking inside those parameters. For example, initially when you started running, say a year ago, your timing was you took say 10 or 11 minutes, 11 seconds to go for 100 meters run. But now you're taking 5 seconds, and it's going lower and lower. It becomes more distinct and apparent as the time goes by. There are some other features, like how do you know if your data is continuous or not? Similar to the discrete one, it has few characteristics, such as it has to be numeric and distributed over data and time. It has the data changes over time and can have different values at different time intervals. And the continuous data is made up of random variables, and it may or may not be a whole number. That is, it can also be decimal numbers. Continuous data can be used for analysis methods such as line graphs, screws, etc. And regression analysis is one of most common types of continuous data analysis. So for this continuous data distributions, we are going to look into two types of distributions: student t distribution and chi-square distribution, which are kind of the most famous ones. And not going too deep into the mathematics and all, I'll just go about, like, I'll give you an overview and with an example of what student t distribution is and where it can be used, rather than going too deep into the explanation and formula and mathematics. So this t distribution is usually used to calculate the population parameters when the sample size is small and when the population variance is unknown. So how is unknown, and because it was penned under the name student by W.S. Gossett, it's called the student's t-test. It's as you can see from this example, like the graph, it looks a lot similar to the normal distribution, right? So normal distributions, t distribution is used instead of normal distributions when you have small samples, and usually including t-scores. The larger the sample size, the more it looks like a normal distributions, and the sample size larger than say 20 can look more like closer. It can go closer to normal distributions. And the degree of freedom, of course, also have some part in it. And degree of freedom is the estimate of the number of independent pieces of information that went into calculating the estimate. For example, if there were like 20 is the sample size, then the degree of freedom would be like n minus 1, 20 minus 1, 19. And some of the basic characteristics or properties of t-distribution includes it ranges between negative infinity to positive infinity. The larger the value of the degree of freedom is, the closer it is to the standard normal distribution. This implies that for different degree of freedoms, the shape of t-graph also differs, as you can previous graph. Okay, the peak is less peaky than normal distribution, but it has more of a longer tail going to the sides, and the peak is like highest attains when mu is equals to 0, and the same from the diagram. And the distribution is the mean of the distribution usually ranges is equal to 0 for any degree of random variable degree of freedom more than 1. If it's more than 1, then mean is usually equal to 0. Otherwise, it's undefined. Sorry about that. Okay, so here are some of the examples of this. When can you use t-distribution? Statistically, t-distributions are used to find the critical values for a confident interval when the data is approximately normally distributed. What are these critical values? These are like the starting and the ending point in that confidence interval we are talking about. That's critical value. Finding the corresponding p-values for statistical tests that uses the t-distributions are some of the statistical way of saying like where it's being used. But another simple example would be, say you have sampled 20 students with 2 different classes to estimate the mean standardized test scores for each of them, like each of the class, and you want to use the two-tailed t-test, and you find out that the class 1 and class 2 has something like the t-score is 4.61 with 95% confidence interval of 3.87 to 5.37. So it looks something, the graph will look something like this. As you can see, the tail is long and the peak is not as rounded as the normal distribution. And it's also seen that because it's not really crossing 0, the numbers are not really crossing 0, it's not going to be too close to 0 and will be further apart to the right. So in a way, it's more like when you want to suggest if something you're working on, if you have a hypothesis, for example, if you have a store and you want to have a new product launch or something like that, you want to compare it, test it out, whether it's good to have it or not. That's when t-distributions can be used. Another method which is also used is chi-square distribution. Chi-square distribution is used for same statistical testing, and it includes usually 2 types of tests, that is chi-squared goodness of fit test and chi-square goodness test of independence. So goodness of fit test is mostly about like telling if the product is fit for you or not. How good is it for you? And we have a set of data values and idea about how the data values are distributed. Then the test gives us a value to decide if the data value has a good enough fit for our idea or not, or is it questionable? Do we go ahead with that or not? Something similar. So for example, if this is the data variance, say the data variance with 3, 4, and 8, it's a degree of freedom of 3, 4, and 8, then we see that higher the degree of freedom of the chi-square distribution, the more it looks like a normal distribution. So this one has 8, it looks closer to normal distribution. Yeah, this is there's a tail and all, but it kind of looks similar to normal distribution. Chi-squared, okay. If you want to look into the example, like real world example, how we can use it, there's an example where we have a candy of 5, a bag with candy with 5 flavors, and we want to test if the proportion of the 5 flavors in each bag is same or not. For example, does one bag has 20 yellow candies, equal proportion of all 5 candies, or does it vary from bag to bag? And another question, another example would be if you are in a team of like children's sports team and you want to see if all the team members, like the children's, have experience or they don't really have an experience of league or playing before, and what's the percentage of it. Again, there are few categories that has to be fit before going into the chi-squared fitness. That is the data values that are simple random samples from the full proportion. Data values have to be a simple random sample from the full proportion. Categorical and nominal, it has to be categorical and nominal. Chi-squared goodness of fit is not appropriate for continuous data. A data set that is large enough so that at least 5 values are expected in each of the observed data categories. So it has to have at least like 5 values in the data set. And if you look into the candy bag example, it looks something like this. So this is the expected value. We were hoping to have like 200, everything same. But now that we looked into it, we just found out that there are more lime and grapes and orange when compared to cherry and apple in the bags, and it varies. In some bags, it's not as we expected. So that's an example of it. So chi-squared, this another test is chi-square test of independence, and independence is a statistical again, it is a hypothesis test used to determine whether two categories, categorical or nominal values, are likely to be related or not. So you can use this test to when you have a counts of values for two categorical values, variables. For example, if you have a list of movie genres, and that's like the first variable for us, and the second variable is number of people for those genre who bought snacks at the theater. For example, if people bought more snacks for horror genre or maybe less for romance, things as such, and we want to look into that. The owner of the movie theater wants to estimate how many snacks to buy, and if based on movie types and snack purchases are related or unrelated, and we want to know deeper on those things. Another example would be in a veterinary clinic where you can find the list of the dog breeds, and the owners who feed their dogs with dry food, canned food, mixed food, so that it's the clinic can use this data to understand the consumption of the what is the best like food intake for each breed of dog and what's the result, and to find out, like chart it out and things as such. Again, this also need to have follow like 3 conditions. That is the data values that are as simple as random sample from the population of the interest. There has to be like 2 categorical or normal variables. Don't use the independence test with continuous variables that defines categorical conditions. And for each combination of the level of 2 variables, we need at least 5 expected values. So it's almost the same. And this is an example for the like movies plus like movie genres and the snacks bot. Now, I know it might have been very confusing so far, especially the chi-square test for independence and for t-test like distributions. We have talked about chi-square distribution and t-distribution, when to use that. When we use chi-test for independence, we are usually, when you say when you reject a null hypothesis and you say that, okay, whatever hypothesis it was, say for the candies in the bag, it means that there is a significant association between the 2 variables, whatever variables you chose at that moment. And when you for t distribution, when you reject it, it means that those are not really the 2 population means are not really equal. What does that mean? So for example, if you have 2 variables and both are categorical, say for example, categories such as they can be fit into male, female, Republican or Democrat, anything as such, then it's better to use chi-square test. But if you have only 1 variable which is categorical, example study plan, either plan 1, plan 2, something like that, and other is continuous, say exam score, which can be measured between 0 to 100, then it's better to use a t-test for that and go with the t-distribution for that. Here are some of the parting thoughts and useful resources. I'm sorry I didn't take much questions, but I didn't see any questions popping up, so I didn't stop for them. But if you have any questions, please feel free to ask me any questions, and that'd be great to have. Thank you for having me today. Anjali.
Hi, Shaistha. We have one question. So how is Bernoulli distribution similar to Boolean distribution?
Boolean binomial distribution. I think it's binomial distribution.
Okay.
If you Bernoulli distribution, when I say Bernoulli distribution only happens for one event, right? If you want to, when I say one event or one trial, it's like only for one coin flip, that's like Bernoulli. And if you want to go for say 50 or 100 coin flips and you want to see the success rate and you want to compare it and go deeper into that, that's when you want to go for the binomial.
Okay, Shaistha, that's all for the questions. Thank you so much. And
Thank you.
so that's all for the session here.
Thank you for having me today.
Thank you so much for the audience being so engaging and active.
Thank you so much, everyone, for joining today. It was a great, great session. And thanks to our speakers, Sneha and Shaistha, for this amazing explanation. And thanks to our host, Anjali, and all the moderators that helped today. And the recordings of the previous session in today's session will be very soon uploaded in YouTube and will be shared with you all. Thank you so much. See you in next session. Have a great weekend.